Hi, my name is Skylar Mell, and today I will be presenting Lab 2 of Physics 2212, which is lines of charge. The purpose of this lab is to estimate the charge found on a tape strip, this time improving our charge model. In Lab 1, we modeled the tapes as a single point charge as shown to the right, yielding an approximate charge of negative 1.2 times 10 to the negative 8 coulombs. In this lab, we will more precisely approximate this charge by modeling tapes as a distribution of charges on a line where the charge was found to be negative 6.5 times 10 to the negative 8 coulombs. The concepts we will be using will be Coulomb's law, which relates electric fields and forces with charges at a distance, and distributed charges, which involves the superposition of infinitesimal charges. To replicate this experiment, I created the U-tape by quickly pulling a tape strip off of a base tape shown in Figure 1. Ensure the tape is negatively charged by rubbing a plastic pen and observing repulsion with the tape. Repulsion is necessary because attraction can still occur between a charged and neutral object. Repeat steps 1 and 2, creating 2 total U-tapes. Then lift one tape under the other until the top tape floats, shown in Figure 2. Finally, record the distance between the tapes for later analysis. To model a line of charges, let's split the tape evenly into n individual charges, each with the charge of the tape's total charge over the number of sections. Like in Lab 1, the electric force on the top tape must fully balance out gravity for the top tape to float, as seen in the white and yellow vectors. Also note that our models become more precise as the number of linear charges increases. To trust this model, we need to make the following assumptions. The charge is evenly distributed across both linear tapes. The tapes hold the same total charge. We can use the tape's total length to approximate the mass. The tapes lie perfectly horizontal, and we can ignore air resistance. From Lab 1, we know that both tapes' lengths are 0.231 meters, tape width is 0.0225 meters, and the distance between the tapes when floating is 0.024 meters. The previous approximated tape charge is negative 1.2 times 10 to the negative 8 coulombs, which is found by solving for charge in Coulomb's law expressed below. The strategy for calculating the tape charge using our new model using glow script is as follows. Let's first assume the charge from Lab 1 is correct, then we iterate over infinitesimal charges to find the net electric force on the top tape. Let's compare the magnitude of this force with that of gravity, and finally adjust the tape charge accordingly so these magnitudes become equal. Now let's take a look at the glow script code. The function line charge divides a line into n equal sections, each with the properly scaled charge. These lines are also visualized in the rendering. Now let's calculate and visualize electric fields and forces. For every charge in the top line charge, let's iterate over each charge in the bottom line, summing each electric field for that top charge. Then sum these net charges for each top charge to find the net electric field on the top tape itself. This is best accomplished by nesting 2 for loops and computing net vectors by leveraging vector addition at every step. Finally, I adjusted the tape charge so that the electric force on the top charge balances out gravity. We can find the proportion of the current force magnitude to that of gravity, which is about 18% in this case, because Coulomb's law has a positive linear relationship between charge and force. We can adjust the tape's charge by dividing it by this proportion. This leads us to find a new adjusted total tape charge of negative 6.5 times 10 to the negative 8 coulombs. Note that these calculations only yield approximations, still we can increase the precision of these approximations as shown. Increasing the number of charges on the line increases the precision of our calculated charge. To make an exact calculation, we need the value n to approach infinity. This is difficult for computer environments like GlowScript to accomplish since they can only sum a series to a certain degree. Instead, to get the exact calculation, we need to transform the series of charges and vectors into an integral, where each small charge q becomes dq, an infinitesimal charge that cannot be numerically expressed. Now to reflect on this lab, I'm going to answer the what if and why questions. To answer the what if question, my single point charge model yielded a tape charge of negative 1.2 times 10 to the negative 8 coulombs compared to negative 6.5 times 10 to the negative 8 coulombs, with a line charge model accounting for 442% increase in estimated charge. To answer the second question, the line charge model takes into account the distance between every infinitesimal charge, not just the 2 simplified point charges, so greater charge is needed to span all that distance with an equal electric force. The line charge yields an estimate closer to the real value because it is a more specific, realistic model that makes less dramatic assumptions.